Good morning, all of you. Good evening. Sorry, good evening, all of you. And I welcome you to the present ASTRO ADDA today. So, after some time, we are again doing this ASTRO ADDA program. We used to do this quite regularly during pandemic and after that also. So today we have a very good speaker with us. I'll just introduce the speaker before we start the program. So we have Dr. Sathya Narayanan K, who is an IUCAA visiting associate since 2020. He has completed his PhD in astronomy and astrophysics from Amrita University in 2018, and during which he collaborated with Professor Jan Murthy at the Indian Institute of Astrophysics, Bangalore. Since 2019, he is a faculty at the Department of Physics, the Cochin College, Kerala. So today he will be speaking um, a very interesting topic, that is exploring the universe from curiosity to a career. So I would invite Dr. Sathya Narayana to please start his talk. Can you hear me?
Yes, sir. Can you hear me?
Yeah. You can start. You can make
Okay,
your
sir. I hope I can keep my video off because raining is here. So,
yeah. You
okay.
can make it full screen. It is not full
Yeah,
screen.
sure, sure.
So we can have the talk, and after that we will take the questions. So
Okay, so you can hear me, all can hear me and see my screen, right?
yes.
Okay, fine. Thank you, Regional Science Center and Planetarium Calicut, for inviting me to this session. And special thanks to Jayan sir. Today, I will keep things very simple. I will start with an introduction to astronomy, and I will touch an introduction to computational astronomy as well. So I hope there are a wide range of participants here, from school students, plus two UG, PG, and other general public. So I will keep things very simple. Uh, so astronomy is a fascinating topic to majority of the people, and the main thing is astronomy. When compared with other subject, astronomy is the oldest science. When you go back to history, we can see that astronomy is not a business started 10 years back, 100 years back, or even 1000 years back. So here you can see in the picture on the left top, Stonehenge. It is a world famous monument in England. It's recorded. It's recorded that it's at least 5,000 years old. Now, not only in a single civilization, almost all the famous civilization like Mayans, Egyptians, or Indian, Greek, Chinese, everyone, they were fascinated about astronomy. So this in Egypt, you can see the pyramids are world famous. We can notice that these pyramids are not just tombs. There were strong connection with astronomy. And in the case of Mayans, here I don't know how to pronounce this monument name, but in the case of Mayans, this is also very famous monument. For Mayans, it was closely connected with religion. All their rituals, all their ceremonials, all their farming kind of things were connected to astronomy. And the middle picture, many civilization I have shown in this picture. The central one is the Jantar Mandar in India. This is not a prehistoric monument. It's an 18th century thing built by Jai Singh, but it connects ancient Indian astronomy to modern Indian astronomy. So in that case, in that way, Jantar Mandar is very relevant, important. Okay, so the point is, astronomy is not the one of the, it is the oldest science. So even in ancient term, people were grouped stars, which looks like, uh, which forms a pattern or shape in the sky. Uh, here I have shown few famous constellation in the sky, like Orion, the Hunter, on the left top, the Ursa Major, Great Bear, Scorpius, Scorpion, Cygnus, the Northern Cross. All these constellations are very famous, and there are a number of constellation. Officially, there are 88 constellation recognized by International Astronomical Union (IAU). Okay, so one point is, though in appearance they looks like closely attached, the stars that forms the shape may not be at the same distance. This is just a two-dimensional projection only. So that's the point we need to understand. Now, the constellation through which Sun is moving in a year, we call that as zodiacal constellation. There are 12 zodiacal constellations. Sun passes through 12 zodiacal constellation in a year. That name is shown here. In Malayalam, you will say Medam, Idavam, Midunam, Karikam, the same thing. Aries, Taurus, Gemini, Cancer, Leo, Virgo, Libra, Scorpius. Scorpius means Vrishchikam. Okay, so zodiacal constellation means the path through which Sun moves, that constellation. Okay. Now, when we started astronomy as a science, these were the few people, Western astronomers, I would say, few people who really contributed to the evolvement of this science. So, Ptolemy, who put forward the geocentrical model means Earth as the center of the universe. Then comes Copernicus. He reformed the view like a heliocentric model that says Sun is the center of the solar system and all planets like Earth is revolving around Sun. Then came Tycho Brahe in the 16th century. Tycho Brahe started taking observation in a systematic, precise manner, accurate manner. With a setup at that time, it was very sophisticated one at that time. So in Denmark, he consulted this constructed this setup and actually observed a huge data of planetary motion, solar planetary motions. So he could not analyze those data, but he took those data in a very systematic manner. He started astronomy as an observational science. So sometimes people call him a father of observational astronomy. Then comes Kepler. Kepler actually believed to be an assistant or student of Tycho. He deduced famous Kepler law, three Kepler's law. Oh, then this Galileo Galilei, the Italian scientist Galileo Galilei, who used telescope to observe the night sky. So Galileo was not the one who invented telescope. If I remember correctly, the person who invented a telescope, his name was something like Lippershey or something like that. Galileo used the telescope to observe the sky. And he observed many important things like moon has craters and mountains, Jupiter has four moons, and sunspots he could observe. Then Venus has faces similar like our moon. He observed these important observation, and because of that he had to face trouble in his life. Okay. After Galileo, Isaac Newton came. Isaac Newton's famous law of gravitational attraction, F equal to g m1 m2 by r square. With that, he could explain the falling of apple in the earth and the revolving of moon around earth, revolving of earth around sun. This all can be explained by this single gravitational force of attraction. Okay. Um, uh, I thought to mention many times we didn't acknowledge the ancient Indian astronomers' contribution. So I thought to show this slide. Uh, Actually, it started from Lagda, whatever you call it, Lagda Maharshi or Lagda Muni. He laid the foundation for Indian astronomy, and then Aryabhata, he's author of Aryabhatiya. Actually, Aryabhata could find that Earth rotates on its own axis even before Copernicus, who introduced heliocentric model. Then Varahamihira, he was Varahamihira. What his contribution was, he integrated the idea of Greek astronomy into Indian. That way showed openness to this global scientific knowledge. And he was a strong supporter of spherical shape of Earth. And he claimed at that time that was a very advanced statement, saying that Earth is a sphere and it is standing in the sky unsupported. That was his strong point. Then Brahmagupta actually give a scientific explanation for eclipses than the mythological stories. His many books were converted into Arabic, and the Islamic astronomy were greatly influenced by this Brahmagupta. Then Bhaskara 1 and Bhaskara 2. They were strong supporters of idea put forwarded by Aryabhata. Then Nilakanta Somayaji, maybe perhaps the brightest astronomer ever lived in India. He was part of a school of Kerala School of Astronomy and Mathematics. He used trigonometrical model to predict planetary orbits, and he was many people in the South India were greatly influenced by this Nilakanta Somayaji, and that made Kerala a center for astronomy and astrophysics in a big way. Now, just leave those history, all those things behind. Astronomers usually observe sky with telescope. The first question: why we use telescope? Why naked eye observation not sufficient? That is the main question we should understand. Our naked eye, as a very small lens, it can collect only a small number of photons. The light gathering capacity of our eye is very small. That's why we use telescope to see things in a clearer way and a magnified way. So basically, there are broadly we can classify telescope into two categories. If we are using lens as the primary component, we call it as refracting type telescope. We know that when light passes through lens, refraction happens. That's why we call this as refraction type telescope or refracting telescope. Now, if we use mirror instead, reflection will happen, and that type of telescope we called reflection type telescope. We use telescope just to increase the gathering capacity of photons. It's like placing a bigger bucket in the rain. If you have two buckets with small size and large size, the large size will collect more raindrops. Like that, we use a bigger lens to observe sky objects. Now we have telescope, then why we are using space telescope? We know that we can observe with telescope from ground, but that is limited to when we are observing with our naked eye. That's limited to the visible region only. So unlike other subjects like chemistry or biology or computer, in astronomy, our lab is outside universe. We cannot go there and do experiment and take data. We have to observe the information coming from outside. We cannot do experiment ourselves. Okay, so the information coming from outside space, mainly in the form of electromagnetic waves, that includes many other wavelength also, not only this visible light, that include radio waves to gamma ray, X-ray, violet, microwave, all those type of electromagnetic waves carry information. So if we could observe all those radiation, our information will be more comprehensive. Okay. So the problem is we have an atmosphere, Earth atmosphere. Earth atmosphere, in a way, it keeps the humanity, the human beings alive, the life alive here, because it block the harmful ultraviolet, X-ray, gamma ray radiation. But from the point of view of an astronomer, this Earth atmosphere are blockade. This atmosphere block the information from outside space. So what we do, we place telescope above the Earth atmosphere. That is what we are doing. That's what we call space telescope. So here I have shown the electromagnetic spectrum on the top side. Then there are different telescopes. These are the radio wave. The radio wave can penetrate to through Earth atmosphere, so we can observe radio wave from ground itself. So the left side, I have shown GMRT. GMRT is a giant meter radio telescope. It is situated in Pune. It is managed by NCRA. And microwave, this is Planck telescope by European Space Agency. In the infrared region, there are James Webb Space Telescope by, it's a combined effort by NASA, ESA, and all other space agencies. Then the famous Hubble Space Telescope, it observed the universe mainly invisible. Then NASA's small class mission Galax observed the universe in ultraviolet wavelength. Then X-ray, Chandra is an example for space telescope in that wavelength regime. Then Fermi represent a telescope which uses gamma rays to get information. Okay, now we use computational or we use computational approach to solve astronomical problems. Why? The reason is we have a very sophisticated ground-based and space-based telescope now, and these telescope each produce data of the order of terabyte or petabyte in one day. So if we want to analyze this huge data in hand, we cannot rely on traditional method. We need computational approach. We need high performance computers, AI, artificial intelligence, or machine learning techniques. Then only we can, in an effective way, analyze this data. So remember that in today's time, we are limited by our ability to analyze data. We are not limited by the amount of observation. Earlier, it was the case. We had no observation, enough observation. But today, we are limited by our ability to analyze data. Okay, so that's where this computational astronomy become very important. So in computational astronomy, we solve problem with the help of computer. Okay, so for this, we have to think how we can solve a particular problem from the point of view of computer. That we called computational thinking. Now we have to make a systematic steps, and we have to put instruction to execute what we had through our computational thinking. So to give instruction, we need a programming language. So programming language is just a tool to implement our computational thinking. Computational thinking is more important than programming language. Okay, and if you are a new comer in programming area or computer science, the easiest entry point is learning Python programming language, because Python is easy. You will get a lot of support from net, well documented and future proof. Future proof in the sense, it will not be a waste in future. It will be benefited. It will not get outdated. Okay, all the AIML developed based on Python. So it will always be a useful thing if you study Python programming language. That's why I shown this slide, a single slide entirely for this Python programming language. Nowadays there are so-called no-code tools in astronomy. Here we can do small research thing without much coding or without no coding. Sometimes we may need little code, or so these tools we call as no-code tools or low-code tools. So the examples are given here: Aladdin, Topcat, Orange, DS9, Stellarium, Skyview. Also, we can consider it as a no-code tool. Okay, so if time permits, I wish to show you something that we can do with the Orange software, which is a no-code tool. No code tool, the one you can see on the top right side. Okay, so that's the thing. And for doing this demonstration part, I mean analysis of data through Orange software, I'm just mentioning two or three basic concepts in astronomy, very basic concept in astronomy that will be helpful to understand the telescope data. Okay, so the one thing, very basic thing is, in astronomy, the astronomers measure distance in sky in terms of angle. It will not be in terms of kilometer, light year, or something else. They will measure the distance or size of object in terms of angular size. In the picture, you can see the how it's measured. Here you can see the full moon. You can see two line of sight that connect the top part and bottom part, and this angle represents the size of a full moon. And that is roughly 0.5 degree, will be 0.5 degree. Now if we have two stars, one here and the other here, the angle between this, if we could measure, we will say the angular distance between two stars is 3 degree, 4 degree, 5 degree, or something like that. Now we can use even simpler unit like minute or second. 1 degree is 60 arc minute or minute. 1 minute is 60 arc second, or simply 60 arc second. That are smaller units of angle. Okay, so there is a handy way to measure the angles. It will be useful. So if you stretch your arm, close your fingers tightly and project to the sky. Then the third image at the bottom, the width of that fist will roughly span 10 degree. Then if we open the thumb and the small finger in a stretched manner, it will span around 20 degree in the sky. Then if you place the three fingers, forefinger, middle finger, and ring finger, only that will roughly span 5 degree. Only small finger, that will be 1 degree. So this is the handy method. This will work for all age group, because our body size and hand size are proportional. So this will work for even kids from adults, from kids to adults. So if we have an understanding about the distance measured in angle in the sky, now there is an important concept in astronomy called parallax. In Malayalam, we will say it is sthana brahmam. Okay, so what you can see in this picture, there are two picture, left picture and right picture. Uh, the observer is observing his forefinger with his left eye closed. Okay, the background, you can see a volcano. Now he close his left eye and view the same finger with right eye open. Okay, so now what will happen? this is we can easily experience, or we had already experienced. So what is happening here? So we feel that the object that we are viewing here, the object is the forefinger, it is shifted from right to left. When it is shifting, when we observe from two different position, when we observe the same object from two different position, we feel like the object shifts its position. Okay, so here two position, observing from two position means observing through left eye, in the second case observing through right eye. Okay, so when we observe an object, the same object from two different position, what's happening is the background changes. Okay, so the shift in background makes us feel that the object is shifted. Okay, so this phenomenon, that is the shift in position of object when viewed from different position, is called parallax. This is because when viewed from different position, the background changes. Okay, so from these two figures, we can see that this forefinger shifted to this side. Okay, so this is the distance shifted, and if I can measure this angle, that angle is called parallax angle. Okay, so the same idea we can use in astronomy to measure distance to star. So here, this is the star, the yellow spot is the star to which we have to measure the distance, and this is sun, and earth is revolving around the sun. Now we are observing this star, the same star, from two different position. How we can observe the star from two different position? We don't need to do anything. We have to wait a few months, because if you wait maybe 6 months, the earth is revolving around the sun, right? So if it is in January, after 6 months, we will be in a different position in space, right? So at these 2 points, we will observe the star, and this is the view in January, and this is suppose this is the view in July. You can see that the star is shifted to right, to this left side. You can see that the background remains same. These are the background stars. They are very far away, quite distant stars, so they will not change. The background will not change, only the star position is changing. Okay, so this is the shift. So we can measure this angle. This angle will be equal to this angle, and that is we call parallax angle. Okay, or in mathematics we will say this is half of the parallax angle, but that's a measure of parallax only. So if we could measure the parallax angle using trigonometry, simple trigonometry, tan theta or sine theta, we can calculate distance to this star. Because we know this distance, we know the distance from earth to sun, which is in astronomical unit, we will say as 1 astronomical unit. So if we know this, and if we know the parallax angle, by drawing a right angle triangle and using trigonometry, we can calculate the stellar distance. Okay, now one more important thing, very basic thing, how we locate stars in the sky. Stars or any celestial object. For your convenient understanding only, I'm using the word star. Any object on the surface in the sky, how we can locate. The idea is same, how we locate places in the earth. We use longitude and latitude, right? So the picture shows you how we measure longitude and latitude. The red curve is longitude, This is latitude. In the picture, this spot represent Baghdad in Iraq. So the longitude is 44.2 degree, and longitude is 44.2 degree, and latitude is 33.4 degree. The same idea we can extrapolate to the sky. So we inflate or we expand Earth into the sky, and we will get a bigger sphere here that we called a celestial sphere. Like Earth has North Pole, South Pole, and equator. That expansion will lead to North Celestial Pole, South Celestial Pole, and Celestial Equator. Okay. Now we have a star. All the planets will be moving on the surface, inner surface of this celestial sphere. Now, if we have a star at this point, like longitude and latitude, we will measure this angle, this blue angle and red angle. But we will call it in different name. The longitude will be called as right ascension, and the latitude will be mentioned as declination. The longitude will change from 0 to 360 degree, latitude from 0 to 90 degree if this is in the northern hemisphere, from 0 to minus 90 degree if this is in southern hemisphere. Okay. So this is a coordinate system commonly used in astronomy. The coordinate system name is equatorial coordinate system. The two coordinate system are the two coordinate in this system are RA and DEC. RA stands for right ascension. DEC stands for declination. Okay. Now I will show you a demonstration. So our plan is this: we have to select a region in the sky, a small region in the sky. For this presentation, I will choose Pleiades. Pleiades is Kartika Nakshatra Kutam. Pleiades or Kritika, we will say in Indian astronomy, or in Greek, seven sisters, seven daughters of Atlas. So we will select a region which is Pleiades. Then we have to choose a space telescope data. For the purpose of demonstration, we will download the data from Gaia Space Telescope. We will discuss something a bit about Gaia Telescope. So what we need is we need the data in the Pleiades region where Gaia has observation. Then what we will use? We use a no-code tool, Orange, to visualize the data. That's our plan. Okay. Now this is the Pleiades. It's a cluster of stars. So this is part of Taurus, the bull, the constellation. Why I selected Pleiades? No specific reason, just for our understanding. Also, you can select another region if you wish. There is a region here. It's even in the Taurus region itself, near the eye of this bull's eye. There is a molecular cloud, Taurus molecular cloud. That is an important region where we believe new baby stars are taking their birth. That's also an interesting region. But for the purpose of the present class, I just choose Pleiades. Okay. So this is the zoom in view of the Pleiades. You can actually there are hundreds of stars, people say, but only we can view very specifically, very brightly in 6 or 7 stars. Okay. Now, a bit about Gaia Space Telescope. Gaia is a space telescope launched by European Space Agency in 2014. It observed the sky around a decade. From 2014 to 2025, it observed the sky. It has made 3 trillion observation. Could you imagine that number? 3 trillion. and it includes 2 billion stars and other celestial object. For 2 billion, for 1 billion, you have to put how many zeros? 10 raised to 3 is kilo, 10 raised to 6 is million, 10 raised to 9 is billion. So we have to put 9 zero after 1. Okay. So this is Gaia telescope, and the data is still, I think, as far as I understood, the data is not still fully processed. So the number of observations, the number of stars, the number will increase again. Okay. So Gaia telescope is a very famous telescope launched by ESA. We will say ESA. ESA. This is the logo of European Space Agency, shown here. That now, how to access Gaia data? This is a simple thing. What you have to do is you have to open your Google search engine. Just type Gaia data archive ESA or something like that. Then the first link, this will come as the first link. Then click this link, that will lead to you to this page. This is the web interface of Gaia data. Here you can see home, search, single object, visualization, help tab. There you have to click search. Then you have to give the name here. We will show that. I will demonstrate you that if the internet works. So I have to give the name as Pleiades, but make sure that you are giving the spelling correctly. Otherwise, you will not show this statement here. Pleiades resolved by Simbad. You will not see that. There will be an error. If this comes in a green color and this shows like resolved, it's okay. Then you can see a section here, radius or arc minute. This will define how much area in the sky we have to consider. In the previous slide, we have learned that astronomers measure distance in sky in terms of angle. So Pleiades is a very small region, maybe a 2 minute or 3 minute radius circular region. We may think like that. So in that assumption, I just entered 3 here. This is a drop down menu actually. You will get to know when I do the thing. So this is a drop down menu. If I click that drop down menu, there will come option like degree, arc minute or arc second. Then we have to select arc minute and have to put 3. Then submit query, and we have to download the data. Okay, now this is the Orange software thing. Installing Orange software again is a very straightforward procedure. You have to go to the Orange website, download. If you are using Windows, download exe file. If you are using Linux, download the corresponding file, and that's a very easy procedure. Now when you open the Orange software, once installed, when you open the Orange software, this will be the uh, screen you will be getting. You will get a welcome screen. In the welcome screen, you can see here the video tutorial get started like thing. So if you want to learn Orange from scratch, all the things very basically in simple term explained in this video tutorial section. If you click here, that will lead you to their channel, YouTube channel. Okay. Now I will show you that first. So what we are doing is I will make my screen sharing into full screen mode. Now what I will do is I will open my, you can see my screen, right?
Yeah, yeah, we can see.
Yeah,
Okay, so I just need to type Gaia data archive, or ESA, anything. Okay, ESA stands for European Space Agency, and I'm just entering. the first link, this will come live. Okay, so if there is a window like important notice, just close this, no problem. Then here you can see a few tabs: home, search, single object, visualization, help, like that. There you click search. Okay, then here you give name of the region where you need to get data. Okay, where Gaia has data and you have to download that data. Now I'm writing the name. I should be careful here. I should not make mistake. Pleia. 1 minute. Pleia. Okay, now you can see it appears in green color. Plead is resolved by Simbad. Okay, if that comes, you can make sure that you entered the spelling of that target name correctly. Now you have to select. This is the place. There is a drop down option. If you click the drop down option, by default it will be in arc second. You can change to degree, you can change to arc minute, you can change to arc second. Since we know that the Pleiades is a very small region in the sky, which size is 3 minute, if you consider as a circular region with 3 arc minute radius. So this will be the size. Okay, that's why I'm just giving this value. If you give 5, fine. If you change to degree, you will get the Gaia data in that bigger space, but it will take more time to download. Okay, so I'm just downloading the necessary data only, essential data only, and I will click submit query. I will not do anything, and since it's a very small region, I will get the data. This is the data Gaia has in Pleiades region within 3 minute radius. Okay, so here you can see designation column is there, source ID is there, RA deck. RA and deck will tell you the position of the uh, each star here is represented by a specific unique ID, and parallax you can see here. Parallax will tell you the distance to the star. Then there are a lot of information you can see. You can say PMRA, proper motion in RA. I will not go into all those things. We have just mentioned RA, deck, and parallax. That will be enough. I told you that I will make things very simple for this session. So to download this thing, what you have to do is you can see a download result section here. So the file, the data can be downloaded in many formats. It's your choice. FITS format is there, CSV format is there, WordTab format is there. For the time being, just select CSV. We can download the observation in CSV format, comma separate variable. Then click the download result. So this will result. This will download the result. So this is only 16.6 KB because we have selected a very small region, very small region. If you can imagine the size of an arc minute, you'll be understand how this data is very small. Okay, so by default it will be in your download directory. Once you have downloaded the data, you have to open the Orange software. So Orange software, I have installed the Orange software in my laptop, but I will tell you how. I will show you the site. Orange software, or you can say Orange data mining tool, like that. You can type. If you hit enter, this will be the site. Here you can click download. If you are using Windows, you can download here. Then if you are using Anaconda or some other platform, you can, all the instructions are there. So this in this laptop, it's a Windows, so I have downloaded this version. So if I downloaded that, and I can search orange here, I'm just typing orange. The net is bit low. Okay, so if you have successfully installed the software, you can see the page like this. Okay, then you have to open this. Okay, then you will get a page like this. This one minute. You will get a page like this. This is a welcome page, and you have to close that. Okay, so this is the uh, window you get when you close the welcome window inside that appeared before. Okay, so this is the orange environment. Here you can see a white area. Here we will do all the things. And on the left panel, you can see a certain section. In orange, they call all these as widgets. Okay, first what we have to do is we have to we will say import data. We have downloaded a data from Gaia Space Telescope, right? So we have to import the data. So for that, you just click the data widget section here. Then inside that, just click the file. One time click, that would be fine. So a file emblem will come here in the white working area, and here you can see a small arc thing on the right hand side. Okay, now I have to import the file I have downloaded to this thing. For that, just double click this thing. Then one minute. Uh, this window will pop up. Okay, here uh, choose the downloaded file. Select the downloaded file. Click here, and I have downloaded the file here. This is the downloaded file. I will double click that. Okay, and you don't need to do anything. What you have to do is, please listen. What you have to do is you have to just close this window. So we have imported our data into this file. Okay. Now suppose if we want to see the data, what I have to do is I have to press this visualization gadget. Okay. Just press visualization gadget, and there are a number of plots here. Plots people commonly use in research, not only in astronomy, in any field. So for the time being, I am selecting scatter plot. I just clicked one time, and an emblem for scatter plot will come here. Okay, so I will make this full screen. Okay, Now I have to transfer the data from file to scatter plot. So this is a drag and drop method. Just start from this right arc thing and just click the mouse. A connecting line will appear and drop to the left side. So if you are dragging, if you are taking from right side, it's a input, and dropping left side, it's an out. Sorry, this is input and this is output. Okay. Now the data will be entered in this scattered plot part. Now to see the scattered plot, just double click this scattered plot, and you will see, you can see um, uh, some uh, some kind of plot. You don't need to mind that. Here, just look the left panel here. Here in the axis section, you can select the axis. X-axis is there, Y-axis is there. In this drop-down option, click. You can see source ID, RA, DEC, parallax. Now, if you need to find how the stars are, how the stars observed by Gaia are distributed in sky, I'm selecting my x-axis as RA, maybe longitude. Okay, and y-axis as duck. Okay, now I'm zooming out my plot. Now you can see a list of stars here. So the 1 minute. One minute. Okay, you can see a number of data points here, scattered points here. Each point represent each star in the Pleiades region where Gaia has observed. And if you place here, you can see the RA depth position, its parallax measurement, and all those things. Okay, so this is the spatial distribution of stars in the Pleiades region, where RA is in horizontal axis and DEC is in y-axis. Now, if you want to add more information in the left side, again in the attribute panels, you can see a line color. Now we are going to color these stars, means points, as per their parallax value. Okay, so in the color drop down, select parallax. Uh, you will, sorry, some other thing are coming. So you will get a colored scattered point here. Okay. Now you can see here something here, we call this as legend. So the scattered points here are not same color. Blue color are there, yellow color are there, green color points are there. Now the coloring is based on their parallax value. This is the legend that represent the parallax value. So the yellow colored point is a star or some other object Gaia observed which has parallax in the range 3.5 to 4. The blue points, most of the points, we can see that comes as blue. So they have a parallax value 0 to 0.5 value only. Okay. Now these the circle are in same size. Now if you want to change the size of this thing, you can increase the symbol size, and then what you can do is, uh, in the left panel, again in the size section in the drop down menu, Select size. Again, we are selecting parallax. Now, see how the size of each point changes as per the parallax value. Now here, the circular region, each circular region represent a star, and their radius, the radius of each circle is proportional to their parallax value. So this is a very simple case only. In real case, there will be thousands of stars, and then we plot this thing. We will get instant insight to the idea, or how the behavior of this region, or the properties of stars or celestial objects in this region. Okay, so in traditional way, if we do this the same thing in the traditional way, what we have to do is we have to download the data, then we have to write a program to read the data, then we have to plot the data, then we have to modify, we have to the resizing. If we do manually with programming, it may take maybe 6 months or 8 months, or if you know some programming. Now within 2 minutes you can do all these things. So this is a project. We can do this as a project at BSc level, or even at, if you work on this for a few days, uh, we can consider this as a MSc level project. If you input a few more information or select a much bigger region, a relevant region, like that. Okay. So in this way, this is very simple nowadays. Everything become very simple. That's the point. If you need to work hard, but if you are not smart enough, if you are hardworking only, you may be working a year, but a person who can work smartly, he may be doing the same work within 2 3 days. The so-called these no-code tools or AI tools. Okay, now let me something. Many category of participants are here. So let me tell you something about astronomy as a career. uh, Here, if you choose astronomy as a subject, main subject of your study, you have multiple options as career. You can do a research, you can do research. You will work on data observation, and you will find your own new, you will make new discoveries, and you will publish papers. That is the research career, like as what scientists doing in institution like IIA, IUCAA. People, they are scientists or project fellow, like that. Then there are space careers where you will be more working on space mission, like satellites, how instrumentation can be done, like that. That's called space career. Then in computer career, you will be working as a computer data analyst. You will be learning how to apply recent technologies in AIML to study, classify stars or galaxies. That represent a computing career if you study astronomy. Then there exists education career. You can be a teacher, you can promote science or astronomy, or popularize astronomy, or you can give public lectures, like that. That's education career. And there is another area, industry career. That means if you learn astronomy, the knowledge you are acquiring from astronomy, you can use in other area as well. Because in software companies, other since if you are well equipped with the knowledge of instrumentation, you'll be taken into that organization. Or in the case of telescope, you may get an idea about how optics work, though. So in optic uh, related organization, you may be getting chances like that. Okay, so if you are a school student, if there is any participant here who is a school student, by school student I mean up to 10th standard, you don't need to worry about your astronomy career right now. What you have to do is you have to build your basic science idea, basic mathematics. You have to work on that, and you have to keep the curiosity. You have to keep your curiosity on. Okay, and you can connect to nearby planetarium or moon watching or astronomy clubs like that. But you don't, at this time you don't need to worry about your career right now. Okay, so just build up the right foundation, which is basic mathematics and science curiosity. Now, if you are in higher secondary, the best option is science stream, physics and mathematics combination, because physics, mathematics mainly supported with physics will help you in a very strong manner for your astronomy future. So you should plan like you have after plus 2, you have to do a degree in physics, or ideally a BSc in astronomy, but it's very rare in India. But since the new 4-year program, many papers are astronomy related, so you will get an idea about astronomy very early in that sense when compared to few years back. Okay, and you can try ICER. A few competitive examination are there, ICER, GNS test. So once you pass the plus 2 or pre-degree level, you can try these tests to get enrolled in a very reputed or research-oriented institution. Now, UG ideal stream is BSc Physics, but this is the time you have to improve your skills in Python programming language or any other programming language. If you are comfortable with CPP, you have to work on it. But Python is very simple when compared to CPP or any other language. Okay, so you have to start a little kind of data analysis and writing things. So scientific writing nowadays is not a big problem if you can, if you have a basic common sense of using chat gpt. Scientific writing is not at all a problem nowadays. Very importantly, during summer there will be opportunities, summer internships at IUCAA, TIFR, IAA, PR, this premier institute. Just apply. People, what happens is people will not apply. People think that we think that will not get, and so will not apply. So you should apply. Whether you will getting selected or not, it's a later thing, but you have to apply. So an important thing is you have to start your research career at this point, maybe in a very minimal way. But what happened, people start a project or research when they enroll for PG program after first year of MSc. So that should not be your case. You have to start the research at this stage itself. So you don't need to wait for MSc. So if you are an MSc or MTech student, just focus on the topic in astronomy. I'm talking all this if you are interested in astronomy. Okay, so astrophysics, cosmology. Cosmology is we deal with, we take universe as a whole and study its evolution with time, how it changes, what will happen in the end, like that. So if you are interested in that, do cosmology. Solar physics is very popular in the ADDA L1 mission. Solar physics also is a very scopeful subject. Then these are all some fields you can concentrate based on your interest. So once you completed PG, you can try exams like JRF Gate or INAT. INAT is IUCAA National Aptitude Test. uh, this all test will give you more if you pass this test, you will get PhD admission in this institute with funding, and you can start your PhD, you can complete your PhD. And the point is, when you are doing your MSc, more than marks, it's okay. If you have a 95 percentage mark, that's fine. But if you don't have any paper or any project work, good project work, that's not a good thing. If you plan a career in astronomy, so along with your mark, give importance to your project as well. Maybe I will say, I would say in to that extent, that you have to give more importance to your research or project than your marks. So astronomy is not limited to people who have a degree or with no degree. Astronomy is for everyone. People can learn astronomy from in their own way. Uh, uh, Amateur astronomy is people do things from scratch when they are already grown up. So there are amateur astronomers who later become real scientists. So that's also possible. So in the case of general public, you can try this amateur astronomy and this activity in the nearby places regarding telescope observation. Astrophotography is a hobby people nowadays do. Then citizen science projects are there. Science project means um, we may have to help. We means the ordinary people will get a chance to help scientists to analyze data, to classify data, like that. Zoo universe uh, and there are many platform for citizen science project. Galax Zoo, I don't remember. There are many citizen science project which is open to public. And if you are very much interested, join astronomy clubs. That will be a part of planetarium in most cases. So you can join that. So astronomy is not limited to a particular people, but it's open to everyone. So I will stop here. The point I want to make here is your interest matters, and you have to work very smartly, and you have to keep your motivation on. Okay, so most of the people are by nature, like our ancient civilization, they already have fascination towards astronomy. But there are people who are interested in other topics also. So they should not, if that is astronomy is not passion, they should not follow astronomy. You have to follow your passion, interest. Okay, so you should not follow a particular field just because a majority people are doing, or because it is fascinating to many others, or because of pressure from relatives, parents. So we have to try to follow our passion. So if your passion is farming, just do that. If your passion is politics, become a politician. That will be better. So this is what exactly this Sanskrit quote. So I will stop here. So if you have any concern, comments, anything to share, I will try my level best to respond. So that's it.
Okay, thank you very much. And now we are open for questions. If anybody is interested in asking question, they can directly either write it in the chat box or unmute and ask.
Thank you, sir. A wonderful talk. Absolutely, it was a insightful and great talk to one and all here. Thank you. Thanks again. Thank you, sir.
Hello, sir. First of all, thank you for the inspiring question. I'm a first year BSc student who just completed my first year. So I'm genuinely interested in the astronomy field. So what should I focus on right now?
So if you are a BSc student, you have to make your physics and mathematics understanding very strong, and attend the astronomy related programs. Many in your place there may be people who are regularly conducting astronomy related programs, mainly from IUCAA. So be in touch with them. No matter what the topic, just attend the seminar, programs, workshop, and make contacts with the main person coming there. That will help you a lot. So if you hear many topics, a certain topic will naturally feel suitable to you, or you may attract to some topic, and then you can work on that. For that, you need to attend as many programs you can, and also make contacts. That's the thing I want to say.
And sir, I am a BSc student in FIUGP program. So right now, after my studies, should I focus on PhD directly or can I do MSc in astronomy, sir?
You can do your internship in astronomy related project. Then I think for your UGP program, you can directly start PhD after 4 year, right? After fourth year, right?
Yes, sir. We can.
Yes, but if by that time you have to have a good understanding about the astronomy basics. Then only you can start a PhD level project. So uh, my point is, you have to do you have a as part of your course curriculum, you have to do internship. So do that in astronomy in a with a person you are comfortable with, and then work on this and make that work on that and make that a PhD level subject. That will be a good idea.
Okay, sir. Then if I'm doing an MSc program, will physics or astronomy, which will be the better choice?
uh, I don't know, but if you are in India, I have no idea about an MSc astronomy courses here.
Yeah, in Osmania University, it may be, it is there.
Okay,
Osmania.
then of course, if you have already made your mind, your career should be in astronomy, you have to enroll for MSc astronomy. In MSc astronomy, they will teach you the foundation course that will include mathematical physics and all those classical and all those things, computational thing. But it will be focused on astronomy. So if you have chosen your area, then of course you have to enroll for, if you should try for MSc astronomy.
Okay, thank you, sir.
Sir, good evening. I am Adit. I'm currently pursuing my second year degree in physics. So I am really interested in research. Okay. I have done my first paper around 3 months ago. That was not in physics. It was a language paper. Now I am currently in process of figuring out topics for my other papers. I am currently working on two right now. I have a question that is the amount of paper more important than the topic? I will make it more clear that one of my paper that I'm currently working on is based on material physics, and the other one is based on astronomy. So, should I focus more on astronomy papers or should I focus more on publishing papers itself?
Okay. So I'm thinking, what should I, how do I respond to that question? So what's your aim?
I want to do my PhD in astronomy,
So the answer is clear,
astrophysics.
right? Yeah, then the answer is there, right? You have to publish papers in astronomy. Whether you could publish more, or if you could publish only less, that if you publish in material science, that won't help you, right?
but that will give me a strong foundation. So I could do more research. I could that would give me a strong foundation in research field as well, right?
Okay, but the number of paper, it depends on field. If you are doing research in a theoretical astronomy, the paper will be very minimum when compared to experimental, like material science PhD. They may have 8, 10 publications in good journal, but the theory will have only 1 or 2 paper. So people working in this field already know that. So they will not judge you purely based on the number of papers you publish. The quality matters, and the field you are working, you have completed PhD matters. If it's an experimental thing, you can there will be many papers. But if it's a astronomy or astrophysics related paper, 3, 4 is very large number if it's in good journal.
Understood. Thank you, sir. Thank you.
There is a question from Vinayaka of 7th standard. She asked that where do you find ancient scripts of astronomy, especially by Indian scientists?
Okay, so mm, in one of my slide, I have shown ancient Indian astronomers. There, uh, 1 minute. There, you can see the book by these people: Aryabhatta, author of Aryabhatiya; Varahamihira, author of Brihat Samhita and Panjasiddhanta, and their books are listed here. So if you need original book, this may be the option, but how much you can understand is a question. And people started writing book in the name of ancient astronomers, but whom you will believe, the authenticity of people who write this book is also a question. So it's better to there are maybe I told you the Kerala School of Astronomy and Mathematics. They have restarted this thing. So in that institution, you can contact a few person and then uh, get advice from them. That may be a good option, because if you randomly Google ancient Indian astronomy books in English, you will get an n number of books. So that may not be the actual things. So you have to go back to the people who actually work on this. There are people who work, who done great work on this. For example, people who work on this book written by Neelakanta Somyaji. There are people now in this uh, institution. You can contact them, and by mail, or if they respond, you can get started.
Ashwati K, you can ask your question.
Good evening, sir.
Yeah.
This is Ashpati. I'm currently doing my first year in BSc Physics. So my question is, I have recently started writing articles in general physics, sir. So now I am interested in exploring the astronomy topics as well. So could you please suggest some good topics that the or else some basic topics that the beginners can start for article writing, sir?
If you type, just go to reputed website channel like NASA, ESA, ISRO. They have a lot listed, a lot of project students can involve with. You can work on that. If you feel the project they are mentioning, you are not understanding. That means you have to work on your basic astronomy concept. So once you have a sound background in basic astronomy, then you can go to these website. Again, website only authentic website. Rely on authentic website like NASA, ESA, ESR only. Don't I mean check the website when you read something. Okay, so you will get from the website the basic idea. You have to work on your basic astronomy, then only you have to start the project at this stage. If you are an MSc student, I would have said you have to start now and then learn after starting, but you are first year BSc physics, so you can spend some more time understanding the basic concept. uh, there are basic concept you can understand. There are a lot of website. You for example, UNL simulation. I will show you the thing here. So this is the website, UNL simulation. Here concepts also. Okay.
Okay, sir. Thanks a lot.
Anybody else? Okay, so Jishma ji, what do you want to ask? You can ask.
I was late for this class, so can I get the record? Is there any recorder that I could get?
This is also broadcasted in YouTube. So rscpcalicut.virtual. I will put it in the chat box. You can note it down. You can get the replay there.
Okay.
So if there is no more other question, I thank Dr. Sathya Narayanan to have come here and given a wonderful talk for all of us, and also answer all the questions very patiently. Thank you so much.
Thank you, Arashi Kalikat team, and thank you, Satyam sir. Thanks a lot. Thank you. It was wonderful. Thank you.